If you do any amount of cooking, you're probably familiar with non-stick pans. As their name might suggest, they're quite good at preventing food from sticking and burning, making them a great general-use pan for cooking pretty much anything. Here's a question though, what makes the pan non-stick? Is it the non-stick coating? Yes it is, but we can go a little bit more in depth than that. Polytetrafluoroethylene, commonly known by the commercial name Teflon, is the material responsible for non-stickiness in the vast majority of pans. PTFE was accidentally discovered by scientist Roy Joseph Plunkett in 1938 whilst he was working with gaseous tetrafluoroethylene as an employee of the DuPont company. On the morning of April 6, 1938, Plunkett's team ran into an issue. When they opened the valve on one of the tetrafluoroethylene gas cylinders they were working with, no gas came out. The cylinder was too heavy to be empty, so Plunkett decided to cut it open, discovering a white powder coating the inside of the container. This material was of course polytetrafluoroethylene, as the iron of the gas cylinder acted as a catalyst under the right conditions, polymerizing the tetrafluoroethylene into PTFE. Plunkett would later be transferred to work on tetraethyl lead at DuPont, a fuel additive that increased vehicle performance, fuel economy, and had such a severe detrimental effect on the environment that it raised the average blood lead levels of the United States enough for researchers to conclude that banning its use contributed significantly to falling rates of violent crime. After the discontinuation of tetraethyl lead use, Plunkett would work on a new project at DuPont directing the production of Freon, a refrigerant, and a chlorofluorocarbon, which is a class of compound now banned worldwide due to its depletion of the ozone layer. But let's put Plunkett's fascinating career aside for a moment and focus on his discovery. What actually makes PTFE so good for non-stick pans? Stickiness between two objects is determined by a variety of factors, one of the more important ones being intermolecular forces, or IMFs. Simply put, the strength of forces between molecules decide how strongly they're attached to one another. Molecules only stick to each other if they have compatible IMFs that can interact. This is why water and oil don't mix. Water is a polar molecule while oil is non-polar, meaning the two substances have far stronger interactions with themselves than with each other, causing them to bead up into droplets instead of mixing. There are a lot of IMFs, and PTFE is so effective as a non-stick material because it barely has any. Fluorine is the most electronegative element, meaning it holds onto electrons very tightly when bonded with carbon. This results in a strong, stable, polar bond. Fluorine is so much more electronegative than carbon that it pulls electrons away from it, creating a partial negative charge on the fluorine and a partial positive charge on the carbon. Polar molecules experience many strong intermolecular forces between other partially and fully charged particles, yet PTFE arranges itself into a symmetrical helix structure, with fluorine atoms wrapped uniformly around a carbon backbone. Because the polar bonds are facing opposite directions, the polarities cancel each other out and result in an overall molecule that is nonpolar. Nonpolar molecules can experience three intermolecular forces: London dispersion forces, ion-induced dipoles, and dipole-induced dipoles. All intermolecular forces are based on charge. Opposites attract, meaning that a polar substance like water will have the partial positive charges on one molecule attract to the partial negative charges on another. These charges are based on the locations of negatively charged electrons, which are what actually interact when atoms bond. All three IMFs in nonpolar substances depend on how easily distorted a molecule's electron field is. London dispersion forces occur when the random movement of electrons causes a temporary imbalance. Electrons exist in orbitals around an atom's nucleus. Each orbital is not a set path for the electron, but instead a three-dimensional shape representing all of its possible locations. At any moment, an electron could randomly be in any position within the orbital, and London dispersion forces are caused when electrons happen to be distributed unevenly, causing temporary positive and negative charges. Fluorine is a small atom that tightly holds onto electrons, so the electron cloud of PTFE is very difficult to distort, meaning it has a low polarizability, therefore having very weak London dispersion forces. The other two intermolecular forces nonpolar molecules can experience function very similarly. Instead of relying on random electron movement, these forces happen when a fully charged ion or another molecule with partial charges comes close enough to distort the electron cloud of a nonpolar molecule. And just like before, PTFE's low polarizability resists this distortion as well. Now, if PTFE has so little intermolecular forces, how do manufacturers get it to stick on the pan? Luckily, stickiness doesn't just depend on intermolecular forces, and PTFE application is mostly a physical process. It typically begins with a metal object that's sandblasted to create a rough surface texture filled with tiny grooves. A layer of PTFE can then be applied. It does not interact well with the metal, but it does seep into all the grooves created by sandblasting, which work to physically prevent it from moving. Remember that molecules with similar intermolecular forces are attracted to each other. PTFE bonds perfectly well with itself, and after this initial layer is applied onto metal, more layers of PTFE can easily be added on top. These non-stick coatings are just a coating. If you were to do something like slice zucchini using a butter knife on your roommate's non-stick pan, they probably would not be too happy with you. PTFE is a relatively soft material, and the contact between metal utensil and metal pan is more than enough to scrape away layers of surface coating. Once you lose the coating, you lose the non-stickiness and you're left with just a normal pan. A lot of people are concerned with safety when non-stick cookware is brought up, and there are some things to address. Perfluorooctanoic acid, or PFOA, was a compound historically used in the PTFE manufacturing process. Its role was to aid in polymerization, being added and then later separated from the final product, although it is possible that trace amounts of PFOA remain in the PTFE afterwards. PFOA started getting phased out of the PTFE manufacturing process in the early 2000s due to environmental and health concerns, and it was classified as a carcinogen by the International Agency for Research on Cancer relatively recently. Modern non-stick cookware should be pretty safe, and these same qualities that make polytetrafluoroethylene such a good material for cookware also make it non-toxic and inert, meaning that it'll pass right through your digestive system without any issues if you eat it. There is one small caveat to that though. If you've ever been told to not use non-stick cookware at extremely high temperatures, there is a very good reason for that. PTFE breaks down at high temperatures, starting at 260 degrees Celsius, 500 Fahrenheit, and decomposing into a variety of nasty substances such as fluorocarbon gases. Inhalation of these gases causes a condition called polymer fume fever, or Teflon flu, which manifests with flu-like symptoms such as cough and fever, usually resolving within a day or two. It also kills birds. It's something to do with the respiratory system being different than ours, but I don't really know, and this video is far too long already. Let's roll the credits. Thanks for watching the video. It took me around 2 months start to finish, and every part was created by me with 2 exceptions. My character model is Proportional Low Poly Man by Butler on Sketchfab, and the background music is Glass Structure Dichroic by DOKURO, both of which are linked in the description. All other parts of the video, including scripting, voiceovers, modeling, texturing, and animation, were done entirely by me. The best way you can support me is by subscribing, and I'll see you in the next one.